Okay. Okay. So hopefully you can see the screen. So okay. So today's tutorial is about predictive machine learning, and um, like this basically it's going to be overlapping with tutorials I have before, so it's not completely new. It's basically just we're just for going to be focusing on regression, like on a topic that I already discussed before last week, I think. Okay, so the predictive machine learning, it's usually involves like using historical data or already known data to predict something about the future. So this is like, of course, like from its definition is very obvious how it is used, like its usage in fields of, like, can be in finance, in like for example this week if it's predicting sales, in marketing, in like different various fields where like you want to predict the future depending on the data you already have. And this will be useful, of course, to basically make data driven decisions, and generally just get insight from the data. So like this like just as an introduction, how is it benefits it can be like of course, as I said just now, is that it's improved decision making, increases efficiency, um accuracy, and it can reduce costs in cases where like of course we need to use for like how to like predictions can be helpful in making decisions that can like contribute to how resources are distributed, and or what how to optimize different factors that can contribute to cost. So just thinking about like the different applications, you can just come up with this benefits. Okay, so not dwelling on this so much, but like I mean, you can think about it. Think about the case at hand, or like any other possible cases where it can be used. So okay, moving on from so introduction to how it's applied. Again, these things you have already seen the steps before many times. This is just like how machine learning models are used. You start by defining your problem or by the business understanding, and then you have the step of like data collection, and then the step of EDA, where you are looking at the data, you're trying to analyze the data and describe it in different ways. This can be thought of like so. Like ADA basically is this two or three steps basically together. They are like they can all be called ADA. Um, so um, like then like I was going to just go over all of them, and then I will just be talking a little bit about what is these three steps. Or three actually. All of the rest is I'm going just to skip the first two. Um, so after like the data pre-processing, you have feature engineering, model selection, training, testing, and then like model deployment. And as like maybe emphasized many times that like these steps can be kind of iterative. So I might get from one, like after model selection and training and evaluation, you can go back and do another like feature engineering and go over again these steps, so you can like think of them. Sorry. Um, they are like it's not exactly, yeah, they are numbered here, but it's not exactly that you go from step 1 to 2 and you never go back. It's like it's not like that. It's they are iterative aspects of this. So this is like maybe you remember like the cycle of MLOps, or the cycle of basically that um, data science in general. Like they are all like kind of look, these are part of it basically. Okay, so in the data pre-processing, so already like mentioned before, but just to emphasize, here is a step is where you handle missing data. Um, you handle like you might also deal with outliers, but okay, so handling missing data and how to handling outliers, there are many things to consider when you're doing that. The number, like the percentage of missing data, missing values, where they fall, whether you choose to drop them or to like fill the data with some value, fixed value, or like fill it especially in time series, you can fill it with like a forward filling or like backward, depending in a different order, fill it with the mean, depending on like there are every choice you make has it, you have to motivate it in a way. um Outliers are also, you dealing with outliers depending on what is your interpretation of the outliers. If you think the outliers are a mistake, so you can remove them, or like maybe you think of them like that, just like these are values that don't make a lot of sense, so you remove them from your data. Maybe they represent cases you are not interested in, you can also remove them. Outliers can, in some cases, might be really important and you really want to include them in your analysis, so you leave them in. So depending on your case and like, interpretation, and you have to make a motivated choice. Okay, I think there is a question. It's difficult. I'm facing that how to deal with missing values. Okay, so can you clarify, like, what is exactly? Do you like you are not sure how to handle them? How to like you have missing values and you don't know what specific um, like method to use to handle the missing values, to fill it, to fill the missing values. I suppose yes, you don't want to drop all of them. Okay, scenarios where the okay, so let me just continue with the missing values and we'll go to the outliers. So you're saying that you if you have 50% missing values. Okay, so all right, so your data have many like multiple features, right? So you have many columns in your data set. So is the missing values in a particular column? If like you have a particular column that is missing like 50% of its values, think, is this feature in the column, is it important? Like you really need to have that value, and then maybe because it's missing a lot of values, you have to choose, like maybe you drop like 50% of your data if it really this column is very important. Otherwise, maybe you drop that column just like because you don't have enough information about it. So you drop the column itself and continue with the rest of your data. Um, like if it's 50, like 50% missing values, like maybe filling it is not going to make a lot of sense, right? Um, okay, so okay, so okay, moving from missing values to outliers. What can be scenarios where like outliers are important? Uh, okay, so um, let's say in your like sales data set. I'm not sure. Like I'm just going to make a scenario. In a sales data set, say you have like if you calculate the outliers of your like plot maybe, or like the sales made in a day, and you find values that are really on the outlier, so they are like bigger than the normal values, but you have some kind of like, okay, so I will just mention two scenarios. So like say like you find like a random day where the sales are really much bigger than the other values, and you might think that, okay, I don't have any kind of explanation for why this value is too big, and you suspect that this is a mistake, and then you can remove this outlier value. But maybe if you look at your data, so I'm just like thinking of the outlier is big, it's bigger than other values, but it's not like it's not insanely big that it's not believable, and there is a reason why you think maybe there was a particular event on that day, and you can, like, from looking at the data set, the data, you see like this was like maybe there was big sales on that day, like there was a special occasion, let's say it's Black Friday or something, and then you have a lot of, like, the sales for that day are big relatively, but they are not like believable. Doesn't seem like it's wrong, but it is just for a specific occasion. Still, you might want to, in your analysis, you want to predict just normal days. You don't want to consider these special days like the Black Friday sales, and so you also remove the outlier. Or maybe you want, in your analysis, you want to really predict also the value of these outliers, so you include them. So depending on what you want to do with your analysis and what is your interpretation of the data. I'm just saying this. I hope that I just give you like the sense of how this, and like how you think about it. Like maybe there are other things that you can consider as well, but like I mentioned, a couple of things. Does that make sense to you? Like, does this answer your question? Um, okay, while I get maybe confirmation, uh, some other question about removing the row. Does this not affect the data when predicting? Uh, of course, it's affected depending on what kind of, how many rows you drop. So rows are the, like, how many records are you're considering your data. So if your data is big and you're dropping like a small percentage of rows, you are not really affecting the data set so much. So the predictive power of your models will still be unchanged, more or less. But if you drop a lot of the data, you might reduce the size of the data so much that it's like affecting, like, of course, this is like understandable that the more data you have, the better your model will be. So just dropping a lot of your data will affect the size and affect the predictive power of your model. What else? So as when I was talking about the outliers, for example, removing outliers will, if you like, or removing a particular kind of data might be like, will reduce the power of your model to predict that kind of events, let's say. So the effect is not necessarily negative, depending on how you do this. Okay, I hope this is clear. So if it's not clear, you can just ask more questions. So let's continue. Okay. Yeah, so another thing is, depending on the model you want to use, you might want to do encode categorical variables. That's something we talk about. So some models can only deal with numerical values, So if you are using those, you have to change your categorical variables into numerical variables. So, and you can do this with like there are a couple of ways to do this with um 1000 coding, and so yeah, so like you can just do that. Some models can deal with categorical variables, so you don't actually need to do this. So for example, if you're using decision trees, you don't need to change your categorical variables into numerical variables. Another thing that you might need to do and can be very good is scaling the numerical features. And this is in regression models. When you're doing regression, you like scaling the values and normalizing the values can be, so these are two different things, but it can be important so that like the importance of the of a feature for regression is not swayed by the range. Basically, just saying that the features of a feature is a particular feature, a particular column carries like really large numerical values, while other column carries like a smaller range. Just leaving them as is and like doing a linear regression, the one with the larger values will have a larger effect just by definition. And that is not like, it's not what you want. You want to actually find the actual relationship between these variables. So you might scale the features such that like you remove the effect of having this large numbers and just actually find the underlying relationships. Okay, so this is like what is included in data pre-processing, this step. So yeah, there are some thinking you have to do, choices you have to make, and you have to like always motivate your choices, write them and motivate them. Like I'm choosing to do this because of that too. So that like you have like the flow of how you went through solving the problem is included. Okay. The other thing is the next step is feature engineering, and as you know, this is about creating new features from existing data. So here again, you have to think about the data you have, and for example, here in or like in the challenge document, also you have suggestions for things that you can create. So you have time, and basically you can create features like, for example, say, is this a day of the week or is it a weekend? For example, this can be like an important thing to include. There are other like let me check, like the other suggestions are like the number of days till the holiday, whether it's like we already have like if it's a holiday or not, but this is already in the data set. But like you can calculate the number of days to the holidays and include that as a feature, as a new feature. um like whether it's the beginning of the month or end of the month, something like that. So try to come up with other things, other features to include. So here, like the examples of like there are time-based features, interaction terms. These are like when you take two features and then you like calculate or come up with some interaction basic means that something that depend on two or more features. So like use two features to calculate something new. And aggregations also, like these are can be like counting on moving averages or like something like that. So these are different types of new features you can create. And in feature selection, after like creating features, what also you can do is in addition to creating new features, you can also drop features basically. something that you think is not relevant, you can drop it and identify the most, like what you think is the most relevant features. Okay. See, this is things I can see during the EDA step, like when you are doing this, like you're plotting and you're calculating correlation and stuff. Think, just also consider that, just to emphasize this. I think last time I answered a question about correlation that was not, I haven't, I think I missed something. Remember that when you calculate correlations, the person correlation coefficient is for linear correlation. So it doesn't take into account non-linear relationships. So when you calculate a correlation, that doesn't mean, if the correlation is small, doesn't mean that there is no correlation between these two features. Actually, that are not linearly correlated. So if you still, even if the correlation is small, and you still think this feature might be relevant, maybe you have to consider a non-linear model. So we'll talk about this in the selection of models in a bit. Okay. Okay, so now the next step is model selection. And here, like, we're talking about regression in particular. So okay, I'm sorry. Okay, so you already know what is regression. So in regression analysis, we're trying to find the relationship between one dependent variable and one or more independent variables. So like we're trying to find the relationship between the target, let's say the target variable, and the predictors, which are the independent variables. And there are different models for regression, different types of algorithms you can use to model regression, and they depend on like the type of data you have and the type of relationship that you assume to have between your variables. So like a type of relationship, you can have linear regression for linear relationships. You can have polynomial regression for like polynomial relationships, and you can have non-linear in other kind of regression, in decision trees and stuff. Another thing like you can think about is the loss function. So this is depending, like for different algorithms, they calculate different loss functions. And the loss function is a measure of how good the prediction is. So sometimes it's calculate, like for regression in particular, we are calculating. So the true value of your target variable, how far it is from the predicted value, sorry. So you get a predicted value from the model. It's you basically, the loss function calculates in different ways. It calculates the difference between this predicted value to the actual true value. And the model, the machine learning algorithm, usually what it does is it tries to minimize this loss function. So it makes of course the goal is to make the prediction as close as possible to the actual value in the training. But depending on the definition of the loss function, it has you can have different formulas, and basically like each has its own pros and cons basically. Again, this is just you do this in the model selection itself. When you're choosing your model, you're choosing the loss function usually. Okay, so loss functions can be mean square error. Like this is just like the target minus the target, sorry, the predicted value minus the true value squared. And and it's a mean because it's divided by the number of samples. It's called L2 error loss. Mean is absolute error. It takes the difference and it's an absolute value. And then you have Huber loss, which is basically a combination of these two. And there is a quantile loss, which is what considers like not only like the prediction itself, but like a quantile basically an upper and lower range for the prediction. So you can look this up. Like when you choose a model, you can read how it calculates. But like for each loss function, there are like pros or cons. The mean square error is like smooth, differentiable, and it's basically easier to calculate. But at the same time, it's really affected by outliers so much because it squares basically the difference. So here, this is not outliers like in the data set. These are different outliers, what I'm talking about here. Here in the predictions, the values that are really wrong, the model that the values it predicts wrong, it's going to be to affect the I say have a large effect on the model. The mean absolute error handles the outliers better, but it has a problem of being like less harder to use. And also it's like yeah, it's harder to use because like specifically when when you're using neural networks, mean absolute error is not as easy to converge as like the mean square error. Basically, it takes longer time, or it can like you might not reach the best model basically. So I'm just saying like I'm saying it verbally, but like I hope it's like if it's not clear, but I'm just like you can read about this more if you want. This basically takes the best of these two, and well, I hope quantile loss it basically gives you like yeah, the range for the prediction as well. Okay, so these are just things too for you to know. You like when you're choosing a model, like you have to understand like what kind of relationships this model is you're modeling here or you're assuming between your variables, and what kind of loss you're calculating. And yeah, so for example, the linear regression model, you're calculating a linear relationship between the target and the dependent variables, and like you're finding coefficient for each feature. Basically, this coefficient can also, like later on, you can think about it as the importance of the feature as well. You have decision trees is where like it's not like it takes it follows a tree basically flow where each feature is like at a node, and basically you can take a decision like whether it decides like whether it's important or not. So you can also see the importance of a feature as well in decision trees. Yeah, so we can look up the definitions of each regression model of these. Like there are more, but these are few of them. Yeah, so again, when you do a selection or you try a model, you need to understand like you just the basics of how it works, what it is, what is the underlying assumptions, and the meaning of the output. Okay. Sorry. Okay. Once you like train your model, of course, like once you choose your model, your data has to be you do this a step before you have to split your data into training and test, and basically evaluate your model on the test set by calculating some of the one of the regression metrics. Again, these are already mentioned before, so like for most of them, there's a mean squared error. Again, this is just like the difference between the prediction and the ground truth, squared and mean, like divided by the number of samples. Absolute error is just absolute value instead of the square. There is also the R squared value, which is like so these values are like can have basically any range, while the R squared is from 0 to 1. And 0 like means if it's 1 is the best thing you can have, and 0 means that your model basically just is not better than just predicting the mean. It doesn't like it doesn't make like it's not good than it's not better than just a guess basically. So yeah, so again, when you calculate a metric, you understand what it means, and like to understand like what how well your model is performing. Okay, so and like again, so beside like the evaluation of the performance itself, you can interpret the results, meaning you can interpret like the importance of like, okay, so in the regression we're trying to understand the relationship between variables. So it's not only that we want a good prediction from, this is like the main goal is to get a good prediction for our target variable, so we can predict it in the future. But we also in regression we can also want to understand the relationship between the features and the target, the independent variables and the target variable. And so we can think of like basically do what's called feature important analysis. Basically try to understand like how important each input feature to the output. And this like there are multiple things you can do. We already discussed this last time when we discussed basically SHAP before. And SHAP is like model independent, basically. So it's not about just regression or a particular algorithm for regressions, right? But as we said before, in regression models, there are some that have like, for example, the linear regression, the simplest one. You can already just by looking at the coefficients that the model predict, you can understand the importance of the data, so importance of the features. So if your target variable is y, is equal to like let's say coefficient multiplied by x1, which is the first feature, and then another coefficient multiplied by x2. You can just, if like your features are scaled, the coefficient, the bigger the coefficient in front of the feature is the most important coefficient, right? Some coefficients will be multiplied, some features will be multiplied by a very small coefficient or like almost zero. So this don't matter as well. So just kind of think about it in that way. Correlation scores can also be thought of as like you are measuring the importance as well, but like this you can do like without actually training any model. In decision trees, you can also see basically once you train and like use the decision tree, you can see the importance of the features. Just like this is like happens once you train the model itself. Okay, so there are multiple ways to do this. You like make sure to like to interpret the results to so that like yeah, you see what you can understand. So you are gaining more insight from not only the prediction of the target variable, but actually like understanding the like the underlying relationships that led to this, and how basically the model arrived at what it arrived at. Okay, so there are another step of model deployment, which I'm not going to discuss so much, but there are like basically several options to deploy the model. You can saving the model with, like, for example, Speakle. You can create an API for some model serving. You can containerize the code, and yeah, so the cloud deployment options. So that's basically the whole of all the steps we went through. So if there are there any questions? I'm sorry about this. Yeah, any questions so far? Okay, so yes, so the first question is, are we supposed to deploy a model this week? Yes, you can see that in the Talon document that there is so in task 3, you are supposed to create a model serving API, basically. So this is what you're supposed to do. So, like, follow this. Is there a tutorial about this? Yeah, so you have a tutorial on Monday about API development. So yeah, so this is about that. The other thing you have is so can you show us by a demo how to utilize them? So about what exactly do you? I'm sorry about this. Yeah. Can you? What exactly do you want a demo about? Like, is it everything or you have predictive machine learning? Okay. Uh, See, I have some code here, but it's like I don't think there's enough time to go through all of it. Um, so okay, just give me a moment. Okay, so okay, so just let me share. Um, mm, okay, so I suppose you can see the screen. Um, yeah, so like so consider that I have some data here, right? So this is like a data about it's still so like okay, it's like it has a lot of features, so really I cannot really go through all of this. But okay, so I have some data. It's not exactly the same that I have. And like so like we'll be using basically is scikit-learn to do this. And as a for regression, like there is random forest regressor and uh XGBR XGB regressor, which is gradient boosted regressor. So the important thing that you have to split the data into test and train. So like here in this data set of splitting is 80-20%. And you assume that you go through the cleaning where like you handle the null values and outliers. And okay, so this is the steps of like handling this. Fill the null values with means for some, depending on for some cases. And the data is like it's housing data, so it's like you want to predict the sale price of a house. So basically you have to split the data for the x, the features, and the target is y, the sales price, and drop this from here. Okay, so here I'm doing the split of into train and test values. Yeah, test size is 20% of it. And yeah, so basically the next step will be to train. Yeah, so there are like you have yeah, for random forest regressor. And this is also like it's still also a tree kind of regressor. It's based on a tree regressor. So you need to define some hyperparameters, the number of estimators, the learning rate, and the number of jobs for here. So random state, this is just for like um, if you specify just to make reproduction possible for this. So these are some parameters you can fix basically. And like if you want to really like make the best choice of this, you'll need to do some kind of cross validation maybe to like choose the best value for the hyperparameters. but you can start with some value depending on how long it will take you to run. And yeah, so what you'll need to do is to train and predict on the validation value set, and calculate the absolute error. This is one of the regression metrics, um, to get whatever like the error you're getting. So here we are comparing two models, and you can see one of them is doing slightly better than the other. Yeah, so this is the basic thing, and then you can do like use like for example use sharp to see like which the importance of the features you have. So like once you run it, you like can see how like this feature has a high importance. And yeah, this is like just listed as like in order basically of importance. So yeah, I know I'm not didn't explain a lot of the code, but this is just like the basic thing, like the basic steps. Is this does this like clarify something, or like does it make sense, or does it like come to answer the question? Okay, good. Yeah. Maybe like I will try in the future to like keep the blah 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 part shorter and provide a proper demo. Okay. Any other questions? Like something you want to ask? Like we have 5 more minutes. Interpretation of this plot. This plot, this one, like sorry, this one, the result of SHAP basically. I suppose that's what I'm talking about, right? Yeah. So basically, this is just is the SHAP algorithm just calculates the importance of the impact of features, and the value itself. What matters is the like the relative values. So compare like the value for each feature to the next. So the higher the values, the more important is the feature corresponding to it. Um, it's not there is no particular meaning to the value itself. Uh, Here, like what is the sharp value itself means, but like the higher the value is, the more important the feature basically. So yeah, here this is calculated for each point in the like the test value, the test set. So you can see like there is like a distribution basically, but that's basically the meaning of it. You can read more about what SHAP is, but as I mentioned, like in some for some models, you can see like let's say if we were using a linear regression model, we can just have after training the model, we can see like on the train model, we can just get the coefficients of like let me just maybe can show you an example. Like just like from a reference, not something I. So yeah, let me sharing this, and one second. So yeah, okay. So this is like an article on um Okay, you see my screen, right? So this is an article on like calculating the importance of feature importance in Python. And um, in the case of, let's say for linear regression, using like a linear regression model from scikit-learn, and like after training, like you have model fit here for the training data set. You can get the importance by just getting the coefficients, which is like the model after it was fitted. You can just find this. Let's see. I don't know if it's clear. Yeah. So this step, right? After fitting the model, you can just extract the coefficients that, like, the model when it's trained, it's calculating the coefficient for the linear relationship between y and the features in x. And basically you can see, like, you can plot this, or you can see the values itself. Like for here, let's see, for feature 0, this is the scores. And basically, based on these values, you can just decide, like, okay, the feature number 4 is the most important one. It seems it has the highest coefficient. And the coefficients that the features that they have very low or almost zero, like, yeah, they have features that have zero coefficients, basically. Feature 8 and 9 have a coefficient equal to 0, which means that are not important, really. If for your like 2 and 3 as well, they are not important for your they don't predict your target variable depending on, like, according to this model. Okay. Yeah, so I suppose this, like, is even more intuitive understanding. Okay. Any other questions? Okay. If there are no more questions, I think we can stop here. And as always, again, any other more questions you can ask on Slack. And yeah, that's it. Stop recording. And